we're starting our vector calculus unit. All of the calculus, like differentiation and whatnot you've done in methods, is assumed knowledge for specialists. So product rule, quotient rule, chain rule, how to derive trig functions and all of that is assumed knowledge. But if you forget and need help, let me know. Happy to help you. Because I don't want to plow ahead with stuff that you guys aren't fluent in, and we can take some time to practice if need be. Not that much different though with vectors. There's a bunch of proof in the textbook that we really don't need to go through, as long as we go through this in that to do differentiation on a vector, you just do it on the individual components. So all of this fancy math is just saying the first derivative of the vector is just the first derivative of I, the first derivative of j, and the first derivative of k. It's really that straightforward. You just do 3 separate derivatives. Kind of just like if you had a polynomial or a quadratic, or maybe a cubic, you know when you got like 4 terms adding together and you do them separately in your brain? It's the exact same thing. The difference being often in specialist will sometimes get trig and polynomial terms just in the same vector. So you have to move laterally with your brain, I guess. But that's all this is. Now the notation-wise, especially when we get to kinematics and start doing problem solving relating to time, position or displacement is your normal function. The first derivative indicated by a dot above the r. Keeping in mind, these are vectors. I should be doing this. Little squiggles to indicate they're vectors. The dot above an r indicates it's a first derivative vector, which we're going to go ahead and assume henceforth is velocity. And your double dot indicates the second derivative, kind of like f double dash. R double dot is the second derivative, which is our acceleration. And we're going to go both forward with derivatives to get from position to acceleration, but also later in reverse by integrating to go from acceleration up to position. I guess the hard bit about this topic, this unit, I guess this vector calculus part, is when we get to projectile motion, which is where, and I think we touched on it ever so briefly, I think Cam was sitting it back and we threw a pen back and forth, and we noted that the pen flew in a parabolic arc with the only force as gravity. Right, we were talking about that. Obviously there are more forces like wind resistance and stuff, but for mathematics' sake, so it's not too hard, we just focus on gravity. So often when we're modeling these problems, we just start with the acceleration, and that's only going to be gravity in a downward motion. Typically, we only work with i's and j's. With projectile motion, we look at 2D motion, not in the third dimension, which is nice. But nevertheless, let's just get on with some practice. I'm going to do the first one, get you to do the second one. We'll look at third together because it's going to have a chain rule in it. If you're super confident, by the way, feel free to just go ahead and work through these. But for those who aren't, let's work together. So in what we're going to do, I haven't written the question. For all of these, I'd just like us to get the first and second derivatives. So for the first one here, r dot t is going to equal, and notice they're all in terms of t. By convention, we usually look at our vectors with respect to time, hence t. So 20t, to derive that with respect to t, is just 20, just like normal. And that's still in the I direction. Now this, 15t minus 5t squared, just treat it like, if it helps your brain, just treat this like you were deriving this. Except you're doing it with respect to t, not x. But it's the same thing. So to derive this, we would just make it 15. So it's going to be plus 15. And then the 2 comes down, so we've got negative 10x. But in this case, it's a t, negative 10t. And that's all in the j direction. Second derivative, we've got r double dot in the t of t. 20 derived is nothing, so it just goes away. And in fact, we have no I component, meaning this particle is actually not accelerating in the I direction. But because when we derive this, The 15 goes away, but we've got just negative 10 in the j direction. That means that this position that's changing over time, the only force acting on it is negative 10 in the down direction, gravity. We don't approximate to negative 10. I know maybe physics you approximate to negative 10. Maybe on your formula sheet it says negative 10 is g. We don't approximate to that. We approximate to 9.8. Even though it's 9.81. Still an approximation. We go 9.8. By the way, when we get to projectile motion, we're going to be looking at these two directions. Positive I, positive j. So this guy, this position, is going something like this, which is our projectile motion. And the acceleration there, the second derivative, negative 10, is the force heading down in the j direction, which is why it's curving down. Okay, I'm going to pause there. Any questions about the working out or just conceptual stuff?
So, why is it that it's accelerating downwards on your graph, right?
Yep.
Why does it go up when it says it's accelerating downwards?
Yeah, great. So you can kind of think of acceleration as a rubber band pulling in a direction, and think of velocity as myself moving in a direction. So if I had a rubber band pulling me backwards, like around my waist, if I started sprinting, I would go really fast, but then I would start to slow down, and at some point it would get so strong that I start heading backwards, right? So you can kind of think of this downward vector as like that rubber band. If I throw a ball hard enough, it's accelerating down, which just means it's decelerating up, if you will, and its rubber band is pulling it down, and it'll eventually get to a point where it cannot keep going up, and then the acceleration will come down. So if your velocity and acceleration are in the same direction, you're speeding up. I'll say that again. If your velocity, the direction you're heading, and acceleration, the direction you're speeding up, if they're the same direction, you speed up. As in, like, if I'm walking this way, that's my velocity, and someone starts pushing me, I'm going to speed up. If they're in opposite directions, so I'm walking this way and someone starts pushing me, I'm going to start to slow down. But then when they're still pushing me, now I'm suddenly traveling in the same direction as the acceleration, I'm going to speed up again. So your acceleration can be one way, but your velocity the other way, but not forever. Does that make sense? Yeah. Right, any other questions? Cool. So, hands up if you've forgotten how to derive trig functions. Yeah, a few. Okay, I'm going to go through this one. If you're comfortable, go ahead, start deriving. The derive, we've got like a little cycle for trig functions. We've got sine, cos, negative sine, negative cos. The black arrows are derivative. The red arrows are integration. So I'm going to say int or diff for differentiation. So that's a useful one to commit to memory. Sine, cos, negative cos, back to sine again. So if we're deriving cos, we start at cos, we follow the differentiation arrow. It's going to get us to negative sine. So r of t is negative sine of t in the I direction. Now we're at negative sine for the j direction. So we start at negative sine, and we're differentiating still, so we're going to head to negative cos t in the j direction. And then in your k direction, we have 5. Fairly straightforward, that last one. Because we get, so negative sine goes to negative cos t in the I direction. Negative cos goes to positive sine. And that's it. But yes, the derivative of the power is the most important part. We derive the power, in this case it's 1, so it's meaningless. And we multiply by the current function. So r dot t is just going to be e to the t in the I direction. But in the j direction, we're going to have to use the chain rule. So if it helps you, you don't have to do it all within the function that you're currently deriving. You can just in scrap paper derive that or treat it kind of like this. So just as a refresher, your chain rule, you derive the outside function, which just is something cubed. So dy dx. The 3 comes down, and that gets squared. The thing inside stays the same. But I have to multiply by the derivative of the inside. Derivative of the inside is just e to the x. So it's going to be 3e to the x outside of e to the x minus 1 squared. So outside function, inside function, times them together. If you prefer, you can use substitution and like let the inside equal u, and then you're deriving u cubed and blah, blah, blah. But for all intents and purposes, that's what's happening. So down here, I'm just going to replace them with t's. So I get plus 3e to the t outside of e to the t minus 1 squared in the j direction. Let's see you guys do the second derivative of that one, if you haven't yet. More chain rule. And a product rule, all wrapped in one. This one's a piece of cake. Do the I direction. Yep. So your product rule, if you've got two functions u dot v, and like u times v, sorry, not dot, vector habit, u times v, let me just write uv. Then the derivative is going to be u dash v plus u v dash. So derive the first one times the second, plus derive the second times the first. Take your time. I'm going to give you 5 minutes even. So I've seen a lot of successful product rules, and it seems like the sticking point for this one appears to be factorizing out at the end, because there's a bit of trickery around that. So we'll go through this reasonably quickly. We know that the product rule needs u dashes and v dashes. So I like to write off to the side, if u equals 3e to the t, then u dash equals 3e to the t. That's an easy one. And v is this thing. So v dash product rule, chain rule is that. If you're not feeling fluent with that, it might be an opportunity to go back in methods and revisit chain rule. It'll be in your Q-Learn somewhere from unit 2, maybe. All right, so now that we've got u dash and v dash and u and v, we simply substitute it into the product rule formula. So we get dy dt is u dash v, so those two combined, and then we've got plus uv dash. I'm just going to do it down here. I've run out of room foolishly. So uv dash, that's this guy again, times v dash, which is this whole thing. Preferably as one big long line. Now you can go ahead and multiply them together and combine them using index laws. But we're going to pause for a sec, because if you can, it's recommended that you factorize out immediately. It's easier to see stuff when it's all expanded out. So I'm looking at this and I'm seeing both terms, the top and the bottom, have an e to the t minus 1. Technically this one has two of them, but it has at least one of them. And they've also both got a 3e to the t. If you go ahead and just routinely combine terms and just multiply them, and this becomes 6e to the 2t, you kind of like lose sight of the fact that there's a 3e to the t in it. So I would recommend from here, because they've both got those, I would write 3e to the t, that's pulling that out and that out. And I'm also going to pull out an e to the t, take 1. That is going to go ahead and multiply whatever's left. So in this first one, we've pulled out that. We've pulled out one of these. So all that is left is e to the t take 1. Plus. In this one, we've pulled out that. We've pulled out that. So all that's left is 2e to the t. This can stay the same. This we can actually do some combinations. We've got 1e to the t plus 2e to the t makes 3e to the t. So we've got 3e to the t times e to the t take 1 times by 3e to the t minus 1. Now that's not the only way to factorize it. I've seen some different representations. But we probably should go ahead and simplify it if we can through factorization. I don't think I can do anything more. Yeah, that looks about it. So then I'd go ahead and just do that as my double derivative. E to the t in the I direction, and in the j direction I have that whole thing. And then I need a third type of bracket, because that's all in the j direction. Isn't that beautiful?